statistical things? Okay. Section 4.4, let's finish it. Here we go. What's this green thing over here on the side? What's this green thing that I wrote over here? What's this guy? And where did he come from? Does anybody recognize him? There is a slope, technically. Actually, there's two different slopes. Do you guys know what the different slopes are? This guy is a slope of what? Tangent. PS from pre-cal, or even just from us going to motion today. What's another way of describing, or what's a way of applying slope? What is that the same thing as? Yeah. Slope can be applied in an application problem to be describing a blank of change. Rate. Which could be like a velocity, it could be like an acceleration, which is the rate of velocity, etc. But it's a rate. So, rate of a tangent is a rate at one point. One rate at one point. What's on your speedometer at 1 split second? What's going on over here, though? Who's this guy? What kind of slope? It's not a slope of a skimming line. Good, it's a slope of a secant line that cuts through at 2 different points. So this would be at, actually not even at, to be honest. This would be over some sort of like A to B interval. So like from 0 to 5, if you took a 5-hour trip and you didn't like take a break in between and you're trying to figure out your average rate over that time. You were driving for 5 hours, you went a certain distance. What would be your average rate? So we have technically our instantaneous rate, rate at 1 instant. We have our average rate over here. Okay, but who is this guy? This is the conclusion, something I can say with what 3-letter theorem from last semester? The function f is continuous on a closed interval from endpoint to endpoint and differentiable on an open interval everywhere in between. And there exists a c within a to b such that f prime of c is equal to f of b minus f of a all over b minus a. And d to c. Not IVT, remember that's the in-between one, the y values. Not EVT, that's the absolute max, absolute min. Extrema, extreme values. This one is MVT, because M stands for what again in math? Oh, we are going to motion, you're right, but actually M in this theorem? Mean, and mean is the same thing as average. There it is. The average is going to be realized by the instantaneous. If your average rate on your trip was 70 miles per hour, whew, hopefully you were going on like up to Bakersfield where the speed limit goes up. If your average was 70 miles per hour, MBT says you had to be going 70 at least once in that trip. Maybe you were going 80, maybe you were going 75, maybe you were going 63. Maybe you got stuck behind a semi for a bit. But still, you had to be going 70 if you were on average going 70. That's the idea of this guy. So, we had an old MBT. What's this guy's name? Oh, guys, it's easy. Just read the page. Yeah! But wait a minute. Okay, so he's mean value? Yeah. He's mean value for integrals. He's mean value with an integral. And you see that this could actually be, well, let me show you. Don't worry about whether or not you can see it. Let me show it to you. I can also rewrite this by dividing both sides by this b minus a. And when I divide them by b minus a, and when I write it in a way that makes a little more sense. Oh my goodness. Come on, back arrow. Thank you. I could show 1 over b minus a times the definite integral from a to b of f of x dx. Or another way of looking at it is the integral from a to b of f of x dx over b minus a, which I could then say is the exact same thing as using my definite integral idea and the FTC, fundamental theorem of calculus, f of b minus f of a all over b minus a. And all of a sudden we come full circle. All of a sudden we come full circle and we're right back at that average. Now, hold on. I didn't show you what was on the other side. If I divided all this over, oh, bummer, my box is going to be too small. Struggle bus, you guys can make it big, right? It's going to equal f of c. It's going to equal f of c. But we just have to get our bearings because you're like, wait. I thought the derivative, yes, the integrand is the derivative of the antiderivative. So we have this quick little reminder from before. Don't forget that the antiderivative prime is little f of x. Or another way of looking at it is the dude in the integral is the derivative of somebody. Who's that somebody? Now, I'm explaining why it works. Try to make it memorable. I'm not sure if that's really helpful. Let's just do an example. Does that sound good? So let's do an example. Forever number 36, we have a lot of forever cards. Forever number 36, we have a lot of forever cards. Let's go ahead and try to solve this number 8 down at the bottom. Now, our books can sometimes be really weird. They say find all the values of x star. That actually might be more of an AP problem. You can think of that as just a special xc if you want. But if I was trying to find the special x's, we can think of them as c's, for which MVT applies. I say, okay, I got a formula, let's plug it in. I got a formula, let's plug it in. And to be honest, I would probably do this one, because this one says you're almost to C. That guy's a little more like stuck. This one says you're almost to C. So I would say f of c, which is the same thing as square root of c, is equal to, so I'm taking this and I'm writing them first, f of c. Who is f? The square root, so square root of c, that's my little f of c, is equal to, what am I supposed to be writing? This dude. F of c is equal to 1 over b minus a, which in this case would be 3 minus 0 times the definite integral from 0 to 3 of f of x dx. Let's write them. So that'd be 1/3, the definite integral, 0 to 3. Why am I writing it x to the 1/2, cool kids? Come on, show off, you got this. The square root is the 1/2 power, and I want the 1/2 power for what rule? Power rule. Power rule says I go up or I go down with integrals. I go up, and when I go up, I'm going to get the 3/2 power. How do I account for the 3/2 power? What do I need to multiply by? 2/3. Multiply by the reciprocal. That's 0 to 3 equaling square root of c. Right? If I'm trying to solve things, I could go ahead and, well, for sake of time, I shouldn't say time, for sake of space, let me come up here. I'm going to have the square root of c. Don't forget about him. He's pretty important. I need to square both sides when I'm done. But I'm going to have 2/9 multiplied by 3 to the 3/2 minus 0 to the 3/2. Now here's something really cool about 0. Ooh, wait a minute. What did I just use to plug in the bounds? What's that special theorem that says this is how you take a definite integral? FTC tells me what? The integral of f of x is... Was that not helpful? Do we need to go back and look? I just want to make sure people know and remember why the 3, why the 0, and if you haven't been practicing, you might not remember it. FTC says I just need the antiderivative of b minus the antiderivative of a. How do I solve this guy? I take my antiderivative, I plug in b minus plug in a. Right? Is that okay? Victor's on it. The rest of you guys alive? Yeah, okay. I know, I see you writing. I'm just double checking on you. If you haven't been practicing, some of this is going to look like, where is she getting the numbers from? But I'm plugging in my b, that's my top number. Plugging in my a, that's my bottom number. But what I was about to say is, what's 0 to any power, cool kids? Yeah, the nice thing of 0 to any power algebraically is just always going to be 0. So all I need to worry about is just that other dude. And do you remember, being nice to your brain, do you remember 3/2 means there's a square root and there's a cubed of that guy. The 3 means it's cubed. The 1/2 means it's square rooted. 3 means it's cubed. The half means it's square rooted. I have a few different options as far as simplifying. One is that I could actually cube that and get the 27 and realize that that's 9 and 3, and then I could square root the 9. So one way is I could think of this as the 27, and then think of it as 9 and 3, and the square root of 9 is 3, 3 root 3. Some of you up here could have thought of this as 3 to the 1.5. Instead of 3 halves going here, which didn't seem to help, 1.5 would give me a 3 to the 1 and 3 to the 1/2. A couple different ways to get there, but ultimately I do get here, and then all I need to do is, well, I would simplify. 3 over 9 is 1 over 3. 2 times 1 is just 2 over 3 root 3. But I still need to get my C. So down here, I just need to get both sides squared. So C is equal to square the 2, square the third, and square the square root. My final answer is, oh my goodness gracious. And all I have to do real quick is double check, is that in between 0 to 3? And the answer is yes. Sorry, the algebra got a little messy there. But once again, I was looking into that blue formula and solving, and that blue formula says, find where the value equals the average value. Find where the value equals the average value. This is average, but this isn't average rate, it's average value. Still MVT, just MVT with like an integral. And this brings us to the end of section 4.4. So as we're at the end of section 4.4, I don't want to totally gloss over WebAssign. I'm going to pause the recording real quick. In case for some reason you didn't get 4.3 finished, just in case you didn't get 4.3 finished, you're going to be asking me for an extension, etc. Remember, we're just trying to have it all ready to go for next Tuesday. I did offer a couple resources in the assignment that you might not have noticed for 4.3. First of all, here is an easier example of what they were asking you to do. Okay? So I did an easier example of the one that they gave you. They gave you one that, I mean, it's actually a really similar problem. It has an x cubed just like the one that you have. What made this one a lot easier is that you were starting at, it kind of shows you where the formula comes from. With yours, you didn't have to make the formula. They did all this work of getting the delta x and everything themselves. But what made this a lot easier was when they plugged in for their little like right Riemann sum approximation thing. Here we go. Oh no. I paused it right after that screen. Okay. When they plugged in, they had a 0 plus because the beginning of their interval was 0 plus. Yours is harder because it wasn't starting here. I think it was starting at -3. So yours was harder because your little a wasn't 0. If your little a is 0, the math gets a lot easier. But this is an easier example walking through from the organic chemistry tutor. Love how he explains things. This was a walking through what they're doing in the sense of, hey, this is a general limit definition of a definite integral. They're plugging this into my function, into my cube, so plugging in that guy to the cube. Then they're simplifying this with multiplication and cubing. Theirs is easier because they don't have a binomial. They just have a single term being cubed. You guys have like a -3 plus, which makes everything harder. But they cube it, and then there's this really special formula for this dude from pre-cal that we didn't technically memorize. That really special formula is what I gave you as the other resource. These special pre-cal formulas about how you can plug in a special formula for I cubed and get out of the sigma, and get out of the sigma, and get out of the sigma. So in your WebAssign, they do this. They make a substitution for your different i's. And then at the very, very, very end, they take a limit as you go to infinity. But this is the limit definition of an integral. So they plug in a formula, they do lots of simplifying, they take a limit in a weird way. I would just say degree test, the limits are tied. And so that would be a 1 times a 1024, and he's about to get to that exact same thing of 1024 as his answer. But those of you guys that might not have gotten this one done, let me get back to your WebAssign. They're doing things like formulas. What is delta x's formula? Then they're doing things like plugging in, -4 to 4. Then they're plugging in your bounds and getting that. And then they're having you use the limit definition to say, hey, remember the limit definition says this guy needs to go to 0. Or you could say n to infinity, but this is a way of saying the little bases go to 0, which is what happens as I fit in more and more rectangles. So a better way of saying that we're more used to is n going to infinity. And then they're doing things like, hey, to get this, I have to steal my lower bound of -4, and that's exactly what makes everything a little bit harder. Otherwise, it'd be exactly like the video that I posted, but you have a -4 plus this. So when you get down to having to plug that into my f of x, plugging it into my function, which was up here, x cubed, the math just gets a little bit harder right here with the cubing. So with the cubing, what you would need to do is, and I showed a couple of you guys this, but I know not everybody can come or does come to Math Lab, and I know that this had a lot of different boxes in it. From here to here, they had to cube that whole guy and simplify. So cubing, I used Pascal's triangle, because Pascal's triangle is the fastest way to cube something without actually doing like foiling over and over again. And so you would have had that a to the highest power, and then that a goes down one, b goes up one, and then a goes down another one, b goes up another one, and then b is at the top. And so what that would look like is you would have -4 to the power of 3 plus 3 times -4 squared times your 8i over n plus 3 times just 1 -4 times 8i over n squared plus 8i over n cubed. This is all you needed for the video that I posted, but because we had the -4 plus, we all of a sudden have all these different terms. And so what this is saying, hey, I'm doing that work and I'm plugging it in after simplifying. So -4 times -4 times -4 is -64. -4 squared is +16 times 3 is 48, and times 8 is 384 with 1i over 1n. And then they keep on going. So they're just cubing the whole thing. Then they take this little guy, the 8 over n, I think is, wait, 8i over n? No, 8 over n. And then they distribute him to everything. And you're like, okay, I'm just going to distribute next. So -64 times 8 is -512. Where's the over n part go? Oh, and they use the sigma formula. The sigma formula says, oh, struggle bus, that's on a different screen. But it says if I have sigma of a constant, the little formula for that sigma would be just that constant times n, and the constant times n over n cancels out, and that's how you get that -512. Then with this next guy, the 8 times 768 gives you the 3072. With I squared over n squared, I'm in the wrong one, sorry. 8 times 384 gives you 3072 over n, the little I guy. We're about to plug in his formula. And you keep on going. 768 times 8 is going to be -6144, and then 512 times 8 is going to be 4096. They're getting this all split apart to where we can go ahead and do what I said about plugging in those little baby formulas of, oh hey, plug in, and oh hey, plug in, and oh hey, plug in. And so they plug in those formulas. However, this next step, they say, yeah, I'm going to plug in, but I'm also going to plug in sigmas and simplify. So this next step, all of this guy is plugging in those, the next guy is plugging in all of those sigmas and then simplifying them. And then finally, you get down. After simplifying all of this, combining all the like terms, distributing, etc., you get down to this little baby's expression of 512 over n. The degree of the bottom wins, and the whole thing goes to 0. Whew! I know there were lots of boxes, but guys, do you have to get every single one of those boxes to get in the 90% to get that full credit? No. But some of you needed more boxes than you got. So, if you want to take a quick picture of the screen, or if you want to come to the recording and watch what I did, you can fill in more of those boxes. Once again, this would not be on the AP, but I gave you one, just one, doing an integral with the limit definition, so that you guys could go ahead and see it, even though we don't have to learn it. All right, as I get back into your Google Classroom, though, that one was theoretically already done, but I know a few of you guys asked for extensions on that. But section 4.4 is the one that I'm trying to support. Now, I did go ahead last year. We didn't have tons of time to do the example. So I do have that MVT example that I just did in class also attached to the assignment if you need to follow an example. But Lucas already asked for number 14. I know at least like it's based on the same problem with number 75. If you guys look at the little numbers off to the side. So let's check this out. Excellent problem. Excellent AP type problem. Okay? Like a possible free response. Maybe not quite with all the different ABCs being the exact same. Free response just means like, hey, it's a long answer with multiple parts, show your work. This is what I don't make a forever card out of it, but this is what we call an accumulator function. Because if I was to go to my graphing calculator, and if I had a function for this, which I technically could do, but it'd be a piecewise. It would be like a y equals 4 for a little bit. Then it would be a y equals, I'd have to use these 2 points to make an equation of a line for a little bit, and then I'd have to use these 2 points to make another line, then use these 2 points to make another line. Like I could make this piecewise function. I would just have a y1, y2, y3, y4 with different x intervals. I could graph it if I wanted to. And as my bounds progress from 0 to whatever they want it to be, if it was 0 to 1, I'd be getting this area. If it was 0 to 2, I would keep adding, accumulating to get there. 0 to 3, I'd be accumulating to get there. 0 to 4, this is called the accumulator function. This would be going negative now. Because as my bounds get bigger, my area accumulates. Area that I make positive, area that I make negative, depending on the above and the below. But when they say g of 0, they're not asking go to 0 and tell me 4. That's f of 0. They want g of 0, g of 2, g of 4, g of 6. They're saying plug it in, which is an integral. I'm plugging into my x spot like I always do in math. And I say, hey, g of x says plug in x. X is not inside the function. X is a bound. So g of 0, I plug in 0, and I say, oh, cool kids, it's a property. Has anybody gotten this property down? If I'm going from 0 to 0, question, what area is that? Yeah, from A to A is always 0, right? I haven't gone anywhere. That one's kind of boring, but if I go from 0 to 2 for the next one, question, what geometry can I use? What geometry can I use if I'm going from 0 to 2? I can do lots of stuff. Do you guys see I could do like a 2 by 2 square and then a 1 by 2 rectangle and then a 1 by 2 triangle? I can do that. Could I do a trapezoid? Kind of, but the trapezoid would only be this part and then that would be a rectangle. I had to split it up somehow. Can anyone give me some part that's in that area from 0 to 2? Someone give me something. What's a shape that's in there? What's an area that's in there? So which one? The square, cool. The square is a 2 by 2, so that would be an area of 4, right? Cool. And then I also have, we're going to do the rectangle next? Rectangle is going to be a base of 1 and a height of 2. Isn't that an area of 2? Right? And then plus, and then I have a 1/2, because it's a triangle, right? This last little piece. A 1/2, 1 by 2. Guys, on the AP, I would beg you to stop there. You have the answer. Now, in WebAssign, might you need to simplify? Maybe. But remember, stick it to the man. You can always just write the pluses and see if it takes it. Maybe. An AP would take it that way because you're totally right. But the final answer would end up being what? 7? If I wanted to go to G of 4, G of 6, G of 8, what am I going to do? Oh, G of 4 is next. Could I start at the very beginning? Yes. But could I also just add on what I know? Yes. I already know 7 because 7 is getting up to 2. So all I need to do to add on to this guy for what's next is just go a little further. And to go a little further, aren't I just adding on that triangle? And adding on that triangle is going to be 1/2, a base of 2, and a height of 2. For right now, for letter A, I'm just going to do a dot, dot, dot. Is that okay? However, quick question. As we get to G of 6, does anybody notice what's going to have to change? When I say I can take everything here, which is going to end up being 9, but why am I going to put a minus even though everything before was doing pluses? Because it goes below. And whenever it goes below, let's see, I have to go to 5 and go to 6. Area above is indicative of positive change. Area below is indicative of negative change. So therefore, my little 1/2 base times height thing would need to be after a subtraction sign. So I take the 0 and the 0 plus, well, 0 is boring, but I do all of that. Then I take the 7 and I do 7 plus, whatever's new. Then I take all of that, which is 9 and 9 minus, because now I'm below. And I keep on going from there. Letter B says, find the largest open interval on which, ooh, forever card time. What's my calculus word, guys? Increasing. Increasing. I look at the derivative, and the derivative needs to be positive. The derivative of who or what? G. So I need to find G prime and say, when are you positive? G prime says I need to take the derivative of G, and the derivative of G. You wrote down lots of forevers yesterday. Did any of them talk about how to take the derivative of an integral? And the answer is yes. FTC part. I can take the derivative of an integral by taking that top bound, right? Taking that top bound, bringing it down, and then multiplying by the top bound prime. Taking the top bound, bringing it down, multiplying by the top bound prime. Bringing the top bound, bringing it down, multiplying by the top bound prime. So when I come over here and try to actually do that in my function, top bound, bring it down, times top bound prime. Oh, hey, G prime is just f of x. Why is that helpful? I actually didn't talk about it being the longest, so I'll just put the longest at the bottom. I probably should have said that earlier. But I'm looking for where, no, not f prime. I need G prime to be positive. So G prime, which equals f, to be positive. And the question is, where is G prime, where is f positive? Why the heck am I circling this even though f is constant and going down on that interval? What does it mean for somebody to be positive? To be in the black, to be in the positives, to be with positive values, positive y's, not negative y's, positive y's. My f is in the positives from x is 0 to x is 4. That's the longest time my x is in the positive. Sorry, my f is in the positive, so my derivative is in the positive. I don't even need a sign chart. I just need to see where it's in the positive. So wait, if G prime, which is f, is positive, meaning G is increasing, question, what is G doing for this part? F is positive, which means G prime is positive, which means G is increasing for all of this. G's going up because I'm adding positive, like I'm adding positive value. There's positive change because of the positive area. There's positive change in G. So it's going up, but slower, 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 slower. It hits a 0. What does G start doing here? Because my F is negative.
Decreasing.
Decreasing. Why am I bringing that up? Guys, if G is increasing for all of this interval, and if G is decreasing for all of this interval, what does this have to do with me answering letter C?
Critical.
There's a critical point at 4. And what kind of relative extrema is occurring at 4? Follow the motion.
Max.
A max. But Victor, how'd you find it? So my function changed from? Did you visualize it? Maybe some people would memorize or think of the memorize and they learned like going from positive to negative. That works also. As far as my G prime is going from positive to negative, and that's because my F is going from positive to negative. But yeah, there's totally going to be a relative max at 4. They're totally like having one lead into the other. G, who is G? He's the integral. Oh, so then G increasing, decreasing, I need to think of G prime. Oh, hey, prime of the integral is going to be the F. I can use this as the graph of the derivative. This is the graph of G prime. Then they tell me to do a rough sketch. That's a little awkward. Because putting it on here, I don't know its initial... Wait, I do know its initial point. I know it's starting at 0. So actually, I know at 0, G is 0. I know at 2, G is going to be 7. No, 7? 6? 7. I know G of 4. G of 2 is 7. G of 4 is 9. Struggle bus, I don't even have enough room on my graph. But then G of 6 goes down 1, so that's going to be 8. So I have some sort of, hey, there's my relative max, and I don't even know it goes down. I didn't keep on graphing, so I didn't need to keep on going. Guys, that is section 4.4, and this was one of, Lucas, that was a great question to ask, or Josh, whoever asked it. Hopefully that helps you out a little bit. P.S. This is number 15 on your web assignment, right? And we can double check like what they're having you fill in as far as boxes, but I'm pretty sure, yeah, they're having you fill in stuff. Maybe you can do the pluses, maybe not. P.S. Make sure when you do the intervals, ooh, struggle bus, I said closed from 0 to 4. Technically, if I wanted to be really precise, F is positive at 0. That was good. But at 4, F is technically 0, which is neither positive nor negative. So I agree with that one being a parenthesis. To be totally technical, this one should be a bracket, but they're doing that whole trick I told you, which is always keep the interval open. Always keep the interval open. They actually had you talk about increasing and decreasing, and if you follow the motion, of course, that's going to be a relative max, and they have you give the point, which you should know from up here, G of 4 is 9, and then make the rough sketch of it. If you have other questions, let me know. We also have a 0 period on Friday, right? You guys could be coming in and asking questions, etc. But how I want to finish class is the motion packet. But now's a good time. Stretch. Stand, take a quick little like pop in the hallway, but don't go too far beyond that because maybe it's cooler and it's stuffy in here. So let's kind of reset. As you guys do, there is another Jamboard to open up to the motion packet. But I actually don't want you to open your motion packet yet. Have it in front of you, have your name on it. But we're going to go ahead and try, which it probably wouldn't be a bad idea. So let's make a section in our notes. We're not going to write the whole thing down. We have the packet on purpose. But we are going to be going to a new Chapter 4B motion. Chapter 4B motion, if you guys want to think about like making your notes. But let me go ahead and put a quick timer on the board. Make a quick round around the room. Just get someone's been trying to plug in stuff to WebAssign that's not working as possible. Hold on, don't go to your packet yet. I want this in your notes because these are all important. I want you to write down position, velocity, and acceleration. So quick reminder, the basic three components of motion. You have position, which is like your distance, not distance, but like where you are. You have your velocity, which is how fast your position is changing, the rate of position. You have acceleration, how fast your velocity is changing. So remind yourself real fast, at the top of your motion notes, we have three main topics: position, acceleration, no, velocity, and then acceleration. And I want you to, maybe not every single word, but get the important ideas down. Initially, colon, what does it mean? At the origin, colon, what does it mean? At rest, colon, what does it mean? Do quick summaries. In your notes, what can you fill in? Put the wrong section, guys? Motion.
Let me put it like this.
Yeah, you guys are writing this down, so we need some of this in our notes. Don't turn in your packet yet.
This is like an Irish jamboard going on.
No. Most of it's in that packet. I just don't want you guys looking at the packet yet because it has the answers.
Wait, what?
The packet has the answers. Don't look there yet.
This?
How many blanks can you fill in?
Nobody really knows.
And if you can't fill in, just write the important words. So write the word initially, write the word at the origin, write the phrase at rest. We're making a chapter 4B motion. It's not an official section.
So is it not part of the chapter 4A?
It is not a specific section in chapter 4. Oh, we are in chapter 4A. I'm sorry. It's not chapter 4B. It's chapter 4A. My bad. It's chapter 4A.
So it's just like
We're making a dedicated section just to motion. But it's not like a specific section from our book. You can fill in what it means. If nothing else, just write the important phrases. Write initially. Write at rest. At the origin. If the velocity is positive, then the particle is moving to them. We're going to start busting things out. But how many do you already? Initially, at the origin, at rest. And once again, Hoban just caught me. I totally forgot we were in chapter 4. Hey, I was doing 4B. We are not ready for that. Alright, here we go. What'd you guys get? First of all, initially, what are we talking about? Initially, what are we talking about? Actually, no.
position.
Nope.
No. Acceleration.
No. What's the fourth thing that's in all of them and behind the scenes in all of them?
Motion.
Time.
We have position, we have velocity,
right.
we have acceleration, but don't we technically have an independent variable of time? At the origin means, did you guys figure out position, whereas at rest means, did you guys figure out velocity? At rest, the rate is 0. At rest, your speedometer is 0, right? Speed, absolute value of velocity. If the velocity of the particle is positive, velocity, ooh, it's like a vector. A vector has both magnitude and direction. Positive indicates something. Do you guys know what positive velocity indicates? Position is increasing. Actually, we don't know acceleration. Meaning, It's hard. Your speedometer only shows positive numbers, so it's really hard to show you like in your speedometer. But think of it this way. Your foot could be,
Right.
cruise control could be on.
I put right.
If cruise control is on, your acceleration is 0, theoretically, right? But your speedometer is still at a number, you're still moving, just your acceleration is 0. So acceleration and velocity, careful, they have like a funny relationship. So not if the velocity is changing, not if the velocity is moving, but if the velocity is just a positive number, why did someone say right? That's in comparison to, what's the opposite way you could be moving? Left. So if the particle is moving to the left sometimes, that would be when the velocity is negative, exactly. Did you look ahead and realize you can sometimes fill in the blank by looking at the next question? So velocity is positive, I'm moving to the right. Velocity is negative, I'm moving to the left. Unless I'm talking about an up-down model. In an up-down model, positive velocity means that thing is moving up. Negative velocity means that thing is moving down. It just depends on whether it's up, down, or right, left as to the positive, negative guy. To find the average velocity over a time interval, we just talked about average rate. Applying that to motion, if I want the average velocity, that'd be change in what over change in time? Your speedometer is measured in what?
Speed.
Your speedometer is measured in what?
Oh, miles per hour.
Miles per hour. The per hour is time, right? What's the miles?
Distance.
Which we're going to call
Position.
change in position, right? Isn't the distance you've traveled 2 different positions subtracted? Right? Over those 5 hours, I traveled from here to San Diego. There was traffic, we'll say that. Pretending, right, from my example from earlier. So I would say, where am I in San Diego? Where was I here? And then subtract the 2 positions. I could figure out my change in position, which would be my distance traveled. So average velocity, change in position over change in time. Instantaneous velocity is x prime of a certain t. Right? Instantaneous velocity. Just take a derivative. If the acceleration of the particle is positive, who is increasing if acceleration is positive? Acceleration is that. Maybe we need to come back here and remind ourselves of the different relationships. Do you guys remember that velocity is the derivative of position? And that's why when velocity is positive, my position prime is positive, which means position is increasing or going to the right or going up. Acceleration is the same thing as velocity's prime. So if acceleration is positive, v prime is positive, which means who is increasing? Velocity. Increasing, decreasing test, remember? That forever card, increasing, decreasing test. If a derivative is positive or negative, then the original, which the original of acceleration is velocity, then the original is increasing or decreasing. Which is why for the next one I'm able to say if the acceleration is what, will velocity be decreasing? In order for a particle to change direction, what must change signs? To change direction, so from right to left or from up to down, what's going to be changing? Velocity, because he's the guy that tells me the right or the left or the up or the down. To be changing direction, it's my velocity that's going to be changing signs. Hey, cool kids, go ahead and turn in your packet to the very first page, and what do you see? Turn in your packet to the very first page, and what do you see? Do you see all the answers to what we just wrote down?
Oh.
Time is equal to 0, position is equal to 0, speed is equal to 0. Well, speed or velocity, so I guess we could say or speed, which is the absolute value of velocity. I just said velocity. Right or up, left or down. Change in position over change in time with a little baby formula. Instantaneous, I need a derivative, etc., etc., etc. However, what do you see at the very bottom of this page? Isn't there a number 11? So what's going on with number 11? Go ahead, turn on in. Number 11. Do you see it? First page has a lot of answers. It keeps on going. Second page has more answers. We're looking at number 11. Are you in the packet? One way to determine what? Total distance traveled over a time interval is to find the sum of the absolute values of the differences in position between all the resting, say what? Between all the resting points. Hey guys, what are resting points based on what we just filled in? When would resting points occur? When what equals 0? Say it louder, someone got it? At rest?
Velocity.
Yeah, thanks, Rocco. Didn't we learn yesterday that there's this thing where we have to think of the zeros of somebody and split up the absolute values? If I check it, if I want to go from an A to a B and I take the absolute value of velocity, if I'm allowed to use my calculator, this will solve for me the total distance traveled. Because this will, from what we saw last time, say I need to think about all the different zeros and I need to split at all those different zeros, which we just said are all the different resting points. And absolute value says, oh yeah, I think about the zeros. I split up the bound between all those zeros, and I say, oh, you moved right for a while, you moved left for a while. I want to take both those distances, make them positive, and say how far I went. Displacement says, well, hold on, you guys ready? Pretend you're going to start an imaginary stopwatch. Tell me when to go. Ready, set. Tell me to stop in 5 seconds. Count down. What's my displacement? Why?
You're back to where you started.
I'm back to where I started. Displacement says, how displaced did you end? I'm back to where I started. My displacement is 0. But what's my total distance traveled? What would you guys have to do? Measure to where I stopped, then add that to the next where I stopped, and then add that to the next where I stopped, and then add that to the next where I stopped. We would just get a Fitbit and say, hey, count your steps, do it yourself, right? But still, the difference between total distance traveled and displacement, total distance traveled says I need the absolute values of everybody. So check it. If I wanted the total distance traveled, this could be a horrible mess if I just have position. But if I have this cool formula with velocity, all of a sudden I have another way of solving this, where I can just take a good old-fashioned, hey, let's derive. With my formula, I'm going to derive. Ooh, do you remember how to derive things? What's the derivative of 1/3 t cubed? Bring down the 3, and then I get a t. And then, what's the derivative of t squared? 2t, and then derivative of negative 3t is negative 3. Derivative of 4 is? Do you remember how I just said you'd have to get a ruler and you'd have to like measure all of my different positions, right? Instead, let's talk about velocity and say, well, when did you stop? When did this function stop? Well, set it equal to 0. Hey, hey. Good old-fashioned factoring. Would you have gotten t minus 3 and t plus 1? And would you have gotten that my stopping points would be negative 1 and 3? How we do in algebra, kids? Come on. Why am I going to say, oh, you don't really matter for my situation. I only want to look here. Why am I going to do that? Because what's the only stopping point between 0 and 6? 3. For total distance traveled, instead of like having to add up all these different changes in position, I'm just going to say I want the definite integral from 0 to 6 of the absolute value of velocity, which is t squared minus 2t plus, no, minus 3. If I was allowed, if this was a rounding of a decimal question, throw that into your calculator with an absolute value. You're done. It'll do it for you. But if we're doing this by hand, we're going to go ahead and use the cool trick that WebAssign doesn't use, right, Josh Young? Bummer. WebAssign doesn't use the cool absolute value trick. WebAssign says figure it out yourself. Bummer. WebAssign would say, hey, is this a positive part of it or is this a negative part of it? And you're like, I don't know, I don't really care. But if you can't do my cool trick of whatever, solve the integral and then add them together with the absolute values of each, WebAssign, sadly, just for you guys to know, for section 4.4, they say, ooh, but when is it below and when is it above? So they would actually graph this little guy off to the side and say, who are you? And if I would go to -1 and if I would go to +3, sorry, -1, +3, if I look at my parabola and see that it's concave up, then I would say that I would need to go ahead and, remember absolute value? Says the positive stuff stays the same. That's going to happen to 6, but then the negative stuff needs to flip up. So in WebAssign, when it has absolute value, it says I need to flip this one because it's below. So it puts a big fat negative there. WebAssign doesn't use my cool trick of make it the absolute value. WebAssign says flip it and put that little negative, not just for total distance, but anytime you see absolute value. Whereas I would say just put absolute value, forget about whether you flip it or not, I don't care. What this would land us back at is taking the integral of our position function, we would land right back at position with 1/3 t cubed minus t squared minus 3t. The plus 4s actually are not going to matter. But I would have a negative, which is going to change the signs of all these different guys because I need to flip it because of my absolute value deal. I'm going to find that from 0 to 3 and say, how far did you go that time? This one doesn't flip. This one stays the same. Put a plus. It needs to be a minus. I'm anti-deriving, but I'm also just saying, hey, I already know what the position is. Minus 3t. I could be putting the plus 4, but those are going to cancel anyway, so it doesn't really matter. Then all I need to do is fundamental theorem of calculus. But what would that end up being? Once again, if you're allowed to use your calculator, life is nice. Because all this messy work of splitting it up and figuring out the changes in position with f of b minus f of a, if I'm allowed to use my calculator, I will get all of that done as long as I know how to take an integral, putting in an absolute value of whatever function of velocity, careful, of whatever velocity function I have, which is going to end up being, I don't need to use t's, I can use x's. It'll end up being 36 at the end of the day if I was to go ahead and solve this by hand. Okay. Total distance traveled says I need to split up at resting points, and if I need to split up at resting points, I need to think about velocity. If I don't have it, I'll find it. So guys, there is a more motion. This is old motion. This is our old motion forever card. This is our old motion forever card. But what do you notice about the more motion forever card? What's here that wasn't here? Yeah, this one had derivatives and like slopes, right? Slopes leading up to derivatives. This one says, oh, hey, remember, we can go backwards, which we've already talked about a little bit with the free fall model and going backwards from like acceleration and things like that in section 4.1b. But we have some other key things to work on as far as speed increasing, speed decreasing, total distance traveled, and displacement. We need to add a few things that only really occur or happen with integrals, which are these guys, and a little bit deeper of an idea with speed versus acceleration. However, feel your packet. It's a little hefty, right? Cool. How many pages did we get through? So, Pause. And let's strategize. I said Tuesday we were having a test, right?
Yes.
We should be listening because we're like, wait, what's happening? Tuesday, I said we're going to have a test, right? Friday was supposed to be our review day, work day. Cool? However, I want to spend more time on motion. We did a lot of WebAssign today, so listen up. Tuesday is a test. But it's not a full test. It's a 10-point test. It's a 10-point test on your forevers. And after your forever quiz on Tuesday, then we will have our test review day, and Friday will be a continuation of the motion day, which means our test is going to be next Thursday. Does that sound good? So one more time. Tuesday, what am I testing you on? Why? We have a lot. We have a lot. And if we can get those forevers down, life will be a bit better. So Friday we're just going to have like around the room forever endeavor. Sorry, you guys don't have endeavors. But Friday we're going to do a quick around the room just to start off class. Do you have to be perfect? No big deal. If you don't know it, go to the back of the line. You'll have another chance. Person next to you will try to fill it in. But get your forever cards up to date for Friday. Does that sound good? Ask me for extensions on 4344 now. Get into WebAssign. Let me know what you need extensions on. Let me give you the extensions that you need. Let's be through 4.4 by Friday. And you're starting to study your forever cards. Friday, we're going to tackle these motion problems. Guys, come with your calculators, come with your forevers up to date, and we'll see how much of the motion we can tackle. Does that sound good? Homework over the weekend will probably be finishing this packet, so it's in your best interest for us to get as much as done on Friday as we can. Does that sound good? Okay. And then Tuesday, one more time. What am I testing you on?
Forever.
And then we get a work day on the review. Does that sound good? Okay. I'm going to go put up that cushion. I'm going to go ahead and change my calendar right now. You guys hang out for the last few minutes of class. Does that sound cool?